Good morning to my fellow prof. My name is Gerald, and today I'll be presenting about my professional internship project, an LLM-based hybrid RAG system for cybersecurity. The goal of this project is to help analysts to ask natural language questions and receive answers grounded in locally stored cybersecurity-related evidence, mainly CVE, common vulnerability and exposure, and MITRE attack techniques. So, I'll first cover the problem statement and the system architecture, then explain the data sources, local model deployment, retrieval pipeline, LangGraph orchestration, and memory agents. After that, I'll also show a short demonstration, followed by evaluation, result metrics, limitation, and future improvements. So, cybersecurity analysts often work with logs, vulnerability records, reports, and behavior descriptions that are not always written in clear identifiers. A user may not know the CV ID or MITRE technique ID, but may describe symptoms such as failed login attempts, PowerShell execution, or suspicious network traffic. Keyword search can also miss these cases, while a standalone LLM may hallucinate if it's not grounded in trusted evidence. So this project addressed the gap by combining local retrieval, ranking, alignment, and also a local LLM to produce evidence-based responses. So at a high level for the system overview and architecture, the user will first submit a query through a chat interface. Then, it will go through a hybrid search implementation through a router, where it decides whether the query is a direct CV lookup, or a direct MITRE lookup, or even a broader analysis query. So for the hybrid search, it will apply to the broader queries. It will consist of semantic and lexical search technique. Then it will go through the database to retrieve the relevant data embeddings. And it will go through the re-ranking process. It is based on their relevance to query in order to improve the precision. After that, it will go through the data alignment for the final retrieved candidates. So let's say if it has CVE and MITRE, they are like both aligned if they are related to ensure semantic consistency and contextual relevance. Finally, they will be output in the LLM, which will generate response based from the grounded verified information. And memory agent will be triggered if, let's say, the user next query is a follow-up. So the two main knowledge sources for my project are CV and MITRE attack. CV provides structured vulnerability information such as affected product, severity, CVSS details, and also reference. The MITRE attack, on the other hand, provides a behavior-based knowledge such as tactics, techniques, detection guidance, and even mitigation. These two sources complement each other because vulnerabilities explain what can be exploited, while MITRE explains how attack behavior can appear in the environment. And here are the two websites that I collected my data. So MongoDB is actually selected for my local database because CTI data is naturally semi-structured. The CV records and MITRE techniques that I collected are in the form of JSON formats, which contains like nested fields, arrays, products, and even optional metadata. So for MongoDB, it excels in solving these constraints. Due to its nature, it lets the system to store this information without forcing everything into rigid relational tables. It also supports text indexes for lexical search, while Facebook AI Similarity Search, handles vector search separately. This gives the system both local storage and hybrid retrieval capability. In addition, it scales very well with large amount of dataset, which is suitable for real-world system deployment. In the current local database, the system indexes about 154,000 CVEs and about 691 MITRE enterprise techniques. So for this slide, it actually shows how I designed my database schema for both CVE and MITRE attack data, which it is a critical step because it directly affects how the retrieval quality. When working with JSON-based data, it is important to extract only the relevant and meaningful fields. If we include too much noisy or irrelevant data, it will negatively impact both embedding qualities and also the retrieval performance. So for the CV document, as you can see on the screen, I structured the data to include key fields such as the vulnerability description, affected products, CVSS information, and also attack vectors. For the MITRE attack, the schema includes key fields such as technique IDs, name, tactics, mitigation, and etc. So moving forward, I choose Quen 3.5 9B as my locally LM because in the implementation, it was selected for its strong reasoning abilities and long context support. So the model is loaded from the local Hugging Face cache using local files only, FP16 precision, and automatic device mapping. The model has two roles. First, it generates the final analyst style answer, and it also acts as a lightweight classifier for tasks such as deciding whether a query is a follow-up or not. So for the advantages, The LLM can be locally deployed due to the sensitivity nature of the cybersecurity query data, and the entire system does not depend on any external APIs. This, in the result, it will ensure the privacy and the data confidentiality. In addition, due to the query model's 9 billion parameters, it actually excels in high reasoning for with the output. So to ensure a smooth and user-friendly interaction, instead of just eyeballing the query output via terminal, a user interface is built with Streamlit as a simple yet intuitive chat workflow. So user can ask about a CVE, a monitor technique, or a follow-up question. Each chat session has a thread ID stored in Streamlit session state, and that the thread ID is passed to the LAN graph. This is what lets the memory component keep context within the same conversation. Then the new chat, the button, reset both the visible message and the thread ID. So coming to the retrieval stage, it actually uses both semantic and lexical search. Semantic search uses BG entry embeddings, and Facebook AI similarity search, to find documents with similar meanings, which helps with vague natural language queries. For the lexical search, it uses MongoDB text search, which is better for exact terms such as CV IDs, product names, and technique keywords. The reason for combining both is that cybersecurity queries can be very mixed. Sometimes the user gives an exact identifier, while sometimes it only describes behavior. In overall, hybrid search gives the system a wider and more reliable candidate. Then after the dense and sparse retrieval, the system combines candidate ranking using reciprocal rank fusion, RRF. Instead of comparing raw face scores and MongoDB text scores directly, RRF uses rank position. So in the implementation as shown in the example, each candidate receives a score based on 1 over 60 plus the dense rank. Then it adds with 1 over 60 plus the sparse rank. This means that a document ranked highly by both search methods can become a strong candidate in overall, while a document found by only one method can still survive if it's ranked well. So in the example shown, if it is rank dense equal to 1 and the sparse also equal to 1, it will produce an overall score with a higher score compared to like if you rank lower. Because if you rank lower, in this example, the denominator will be very large, which will result in a lower score. So after all this, a BGE cross-encoded re-ranker will then compass the query and each candidate together. This is more expensive than embedding search, but it gives a stronger relevant judgment. The final candidate score combines the re-ranker confidence with normalized hybrid strength, using a 70% from the re-ranker and 30% from the hybrid weighting. Thresholds are then applied, so that weak candidates for the list itself will again get removed. This is especially important for irrelevant queries, because vector search will always return the nearest neighbor vectors, even if the query is not actually cybersecurity related. Hence, we need this re-ranking process to remove all the irrelevant or the weak candidates. Moving forward, the alignment stage tries to connect the final vulnerability evidence with attack behavior evidence candidates, if any, when the relationship of two of them is meaningful. For example, a behavior query may return a minor technique and also CVE in the final candidates, which they may be related to each other or not. Then, the system will use the re-ranker to score the candidate CVE to minor pair, then combines the pair score with the candidate's relevance to the original query. If the alignment does not pass the threshold, the system does not force the relationship between the CVE candidate and the minor candidate. This is important because a weak force alignment can be more misleading than showing the evidence separately. Hence, if it's not related to each other, the output is shown separately with no force alignment. So for the LAN graph framework orchestration, it actually organizes the pipeline as modular nodes. The graph starts with memory preparation, then routes the query. It performs either direct lookup or fusion retrieval, and finally generates the answer. For the memory agent, it is grounded in evidence rather than just raw chat history. After an answer is generated, the system actually stores the active topic, a short evidence summary. Then on the next turn, the can classify whether the query is a follow-up or a new topic. If it is a follow-up, the query is rewritten using the previous active topic. It will reduce the focus evidence and it will merge into the grounded answer, which will update the grounding, like the topic plus the summary, and also the evidence ID, if any. If it is a new topic, it will go through the normal pipeline again to retrieve new evidence, and it will become part of the grounded answer. So here I would show a short demonstration of my actual project to show how the user will query, what kind of like different query classes, and etc.
So here is the demonstration for my project, and this is a Streamlit user interface. So the first question I input will be something like direct lookup, and it should show the relevant evidence. If I ask for a question, for example, what are the factors for the shape? Based on the previous granted evidence, it should return the exact section. I can do the same for minor lookup as well. It should return the same thing. Yeah. Let's say if I input based on the description without the ID, what will it return? It will go through the normal pipeline, go through the database, and retrieve based from the description itself, as shown here. And it will also retrieve the relevance like either close CV matching. If I put in for MITRE, for example, this query, it should return for the MITRE techniques well, and other related evidence. Let's say if I put in multiple login attempts by guessing password, it'll return like the relevant technique, which is password guessing, and the other related vulnerabilities. So let's say if I input unrelated random questions, the cake is so ugly, it should return no relevance. Or maybe how to bake a cake, use a double protocol, also no evidence. So what about I put like this, and then I go to the new thread, and I ask for the follow-up questions. There shouldn't be any, because it is based on the previous, like this is a new thread ID. There's no previous groundings.
So, coming to the evaluation metric section, I do not have a ready-made labeled dataset to test in the first place, hence I created my own. In Table 1, I have 6 query classes to test, and their purposes listed here, and the key results are shown in Table 2. So the overall results show that among all the query classes, network log style telemetry mapping is the weakest category because the current project does not yet include a log normalization or log interpretation layer. However, the system performed reasonably well across the other query classes, especially for direct CV lookup, direct miter lookup, description-based retrieval, and general behavior mapping. For Table 3, it evaluated the performance of different retrieval strategies against the query classes. The key result is that the hybrid retrieval gives the strongest raw recall, but it is not the safest final pipeline by itself because it returns evidence for every irrelevant query. The current pipeline, however, with ranking and filtering, has slightly lower raw retrieval scores, but it correctly rejected all the irrelevant queries. This shows that the main engineering trade-off. The best assistant is not the one that retrieved the most evidence, but the one that retrieved relevant evidence and rejected unrelated queries safely. For Table 4, I also evaluate the performance of different LLMs I used. In this setting, the expected ID mention rate measures how often the model explicitly included the corrected CVE or MITRE attack identifier in its answer, when the identifier was the expected label for the query. This metric reflects the answer completeness and identifier preservation rather than the retrieval quality. Although Quen has higher latency than Llama, it performed better in the common rack setting and preserving the expected CTI identifier in the final answers. For the embedding model comparison, as shown in Table 5, BG entry performed better than all mini LM in overall. One likely reason is that BG entry uses 1024 dimensional embeddings, while all mini uses only 384 dimensional embeddings, allowing the BG entry to capture richer semantic information. Moving forward to the future improvements of the system, one key enhancement is that the introduction of a log normalization layer. Currently, raw security logs can be very noisy or unstructured, which makes the accurate mapping of the MITRE techniques more difficult. By extracting structured fields such as process name, protocol, port, and event type, etc., we can significantly improve the quality of the retrieval before the query is passed into the pipeline. Another important direction is the integration of the CTI reports using docklink. This allows us to ingest long cybersecurity reports and chunk them in a structured manner, while preserving important elements such as headings, tables, and metadata. This enhances the system overall by providing a richer contextual knowledge beyond just CV and MITRE data. In addition, we also aim to support multi-source retrieval, combining like CV, MITRE, and CTI reports. This enables the system to provide a more comprehensive and well-grounded response. So thank you. This is the end of my presentation.